Okay, can you hear me, right?
Yes.
Good afternoon, everyone. For me, it's a real pleasure to introduce Marijn van Huis from Utrecht University. He's going to tell us about advances in liquid phase electron microscopy, imaging strategies for soft materials, and control motion of nanoparticles. Well, first of all, Marijn, thanks for accepting our invitation. And whenever you're ready, the virtual floor is all yours.
Thanks for the very nice introduction. Yeah, I think we have a small audience. It's probably due to the beautiful weather and some people having holidays. Probably that's a very smart thing to do. But even smarter is to talk about electron microscopy, obviously. So in Utrecht, we do a lot of in-situ electron microscopy. So that means performing experiments inside a microscope. That means that can be the driving impetus, can be heating, application of electric fields, just exposure to a gas or liquid environment, and other stimuli as well. Here I will talk about liquid phase electron microscopy, which is about the most challenging mode of operation because the electron beam effects are the strongest. So the subtitle is Imaging Strategies for Soft Materials. That goes mainly for the p-NIPAM particles that we are analyzing, and controlled motion of nanoparticles. And those are typically rattle particles. So there is a movable core within a shell, and we can control the motion of this core. Now, in particular, Tom Welling and Albert Grau-Carbonell have been very, very helpful for this presentation. Basically, this is a large part of their PhD work. And I will come to the acknowledgements later. We, of course, have people also who synthesized the particles, and the group leader here is Alfons van Bladeren, who knows everything about electric fields in liquids, also colloidal interactions, physical chemistry, which is all very important if you deal with electron microscopy imaging in liquids. Now, so this is, you can see here below the schematic, what we do to confine the liquid and to shield it from the high vacuum of the electron microscope is to contain it within two very thin silicon nitride membranes. So these are about 15 nanometer thin. The liquid is within, and there is a certain pressure difference, obviously, that leads to some bulging of this area, but it doesn't break, and that gives us the opportunity to image nanoparticles inside a fluid or liquid environment. And typically there is also a flow, which helps to reduce the beam effects, because then you transport away the radicals that you produce by the exposure by the electron beam. Now, first a few words about the Electron Microscopy Center of Utrecht. We are together with the hospital called Electron Microscopy Utrecht. So there is a center at Utrecht University, and there's a center at the hospital, the UMC Utrecht. Together we serve both the life sciences, so the cell biology mainly in the hospital, the biological imaging of proteins mainly at the university. But we do life sciences, geosciences, nanoscience, obviously, catalysis, material science. We take pretty much all samples. And thanks to NEMI, we are also a national facility for analytical high-resolution EM. And if you have any ideas or wishes, or you want to have access to this wonderful equipment, then you can go to our website, www.electronmicroscopy.nl. We can't make it any easier than that. And we also built a new home for the microscopes, a new facility which has a very specialized mitigation for vibrations and electromagnetic fields. So we are part of NEMI, so that is also what this top microscope is from. So it's a €5 million investment from the national roadmap. NEMI is the consortium, and there are flagship nodes where really development takes place, including Utrecht. and there are like user nodes, but we all share the same infrastructure. Now, at our facility, we do mainly, speaking now about material science, we do in situ experimentation. That is really our specialization. We do heating, mechanical testing, biasing, so that means application of electric fields. We can look at battery materials, gas environment and liquid environment, and we work together with Dutch-based companies like Den Solutions, like Thermo Fisher Scientific, like VitroTEM, who is now making gas liquid cells. And we have a team of people ready also who can help you with the experiments and do some service work. Now, that brings me to the real talk. So what we did with liquid cells lately. So this is the system that you have to insert into the electron microscope. So there are tubes connecting, liquids going in, at least one liquid going out. There are options also for heating, and there are options for biasing, so to have electrodes inside the liquid. There are major downsides to liquid cell electron microscopy. There is radiolysis, so you're destroying the water molecules, basically, that leads to all kinds of radicals, so hydrated free electrons, which are extremely reactive. There is an influence on the pH. You create OH groups, free protons, and all of that has some chemical effect on your experiment. And if you really do a bad job, you get bubble formation as well. Now, one other problem is that of charging. So we are containing the liquid between these membranes. But the problem is that these membranes are also being charged by the electron beam that leads to electric fields, unwanted electric fields inside the electron microscope. And this has the tendency, for example, to slow down greatly the movement of nanoparticles. So there have been several reports on movements of nanoparticles. But if you would calculate what the real diffusion should be, like in 3D in liquid, then you would expect things that are many orders of magnitude higher. So very often the reported diffusivity, so the self-diffusivity, let's say the Brownian motion, is 5 to 8 orders of magnitude off. It's really enormous. And actually, nanoparticles are moving so fast that the only way to see them in a liquid cell is to use a very viscous solvent. So either for your smallest nanoparticles, you use a very viscous solvent like glycerol, or you can use water, for example, but then you need to look at bigger particles. So as a rule of thumb, you can say that a particle that is 1 micrometer in size will diffuse over its own length, so 1 micrometer, within 1 second. That means if you make everything 100 times smaller, then the particle will diffuse 100 times faster. And that leads to enormous movements, very high mobility of nanoparticles, and it will fly in and out of your field of view unless you take special precautions. So let me first go here. So the Brownian motion in 3D is something that we have achieved in agreement with theory for 77 nanometer gold nanoparticles in glycerol. Maybe I should turn off the pointer options so that I can play the movie. So these are the particles that we have recorded in the liquid cell. We have imaged that in glycerol carbonate, which is important because there the dielectric constant is very high, and that mitigates the effect of the charging of the electric fields. Now, the fact that the nanoparticles are sometimes sharp and sometimes diffuse is also an indication that there is actually 3D movement. So we have analyzed the self-diffusivity here and found agreement with expectation. So this is part of the imaging strategies, part of the talk. now that we have achieved this, so that we can really track the real movement by nanoparticles, that brings us to the next step, the possibilities to really study interactions between particles, because it is the interactions that allows you to create functional materials, like electronic ink, for example. It is also the interactions that allow you to build three-dimensional structures by means of self-assembly. And let me just move something out of the way. Right. And it also gives you the ability to manipulate these particles with electric fields. So the particles that we have used are rattle particles. They are so called because they are shells filled with core particles. These core particles can move. And everything is filled with liquid. The shells are porous, so that the liquid can also go in and out, and you can change, for example, the concentration of ions or concentration of salt. So that laser pointer, yes. So that also you can change the salt concentration within the shell. Now, these are all TEM images, or this is a STEM image, and here this is a SEM image. Now, in SEM, you typically only see the surface, but SEM has, the electron beam in a SEM has a certain penetration depth. So here you can see subsurface, you can see through the shell, and you can see also the core within. And we have used both gold cores and titania cores. So there are various applications. You can think of lithium-ion batteries for drug delivery, sensing. So these rattle particles all have a certain functionality. For example, you can contain a particular medicine within, and then when it has arrived at the right location, you can destroy the shell, making sure that the drug is delivered at that particular location. You can use this as nanoreactors for catalysis, so for optimum mixing, let's say. You can think of switchable colloidal crystals, switchable in terms of light, because they are susceptible to electric fields. So you can turn on an AC electric field, and depending on the frequency, these particles will take particular positions. And when they are all aligned in a particular position, or when they are moving in a particular position, they will affect the direction along which light is being transmitted or not. And that means that you can make, for example, windows or displays turn black or white. And you can control that with electric fields at low energy cost. Now, first thing that we have to do is to track how can we really manipulate these particles. And the special thing here is that we're moving down to the nanoscale. So these things are known for microscale, but they are never have been studied at the nanoscale. And it gives you really the opportunity to study interparticle potentials also at the nanoscale. And that has never been done before. At the nanoscale, things really change. So this is a new field that we are entering. So the shells are always fixed. I should also mention that the cores are movable, but the extent to which they can move around depends on the electric double layers. So it's simply it's Coulomb interactions. So the shell is negatively charged, the core is negatively charged. These electric fields extend to some extent into the liquid. And how far they extend into the liquid is dependent on the Debye screening length. So there is a particular range in which these electric fields are felt, and that is also determined by the ionic concentration in the liquid. So if the ion concentration is very high, there's a kind of screening effect which makes the electric double layers very thin, and then the core can move around a lot. If the electric double layers are very thick, then the core is kind of fixed in there. So the range of the electrostatic repulsion, the Debye screening length, can be shortened by adding salt. So that is important to keep in mind. And it's also very important because if the repulsion becomes very short-ranged, attractive van der Waals forces may play a role. That means that the core can get stuck at the shell and then it will not move anymore. Then, as we say, the system is not stable, because if it cannot move, then it loses also its functionality. So this is the idea. It can move around as far as this is allowed by the electric double layers. And the idea is now that we can manipulate this. We can manipulate this by adding salt, and we can manipulate this by applying electric fields. So this is then what you see when you record the STEM image. So we do everything with STEM, because simply it gives the best signal to noise ratio when you work with liquid cells. Now, of course, the particle, as I mentioned, so this is quite a large particle, like 400 nanometers, but it even moves so fast that you cannot track it, you cannot image it fast enough. So you get this stripy pattern because of the STEM imaging from left to right. But nonetheless, you get an idea of the area that is accessible by the core within that fixed shell. The point here is that this is a 2D projection, so we have to take into account also that the real motion is in 3D. So this is the procedure. We load the sample in a liquid cell. We flow in demilitarized water for 30 minutes. So that is very important, because otherwise all the remaining ions will mess up your experiment. Then we turn off the flow. We image at the known electron dose rate. And then we flow in the next lithium chloride salt concentration. These are very small ions, so they can get through the shell very well. And then we start to image. And then this is the result. Now, from a very large number of images, we can then track how what is the area that is seen by the core. So this is a raw image just to see what the data looks like. We go, of course, to the very, very minimum that we can achieve in electron beam exposure in order to get the best result, but that we still have enough signal to noise ratio to do some statistics. And of course, the zeta potential here, that is the charge. So that is on the core and on the shell. So we can also measure that separately using electrophoresis. Now, we have checked, of course, the electron dose rate. The conclusion is that for high electron dose rates, you see indeed influence of the electron beam, but at lower electron dose rates, 12 or 45 electrons per square nanometer per second, the influence is very limited. We chose in the end to go with 45 because that gave us sufficient signal to noise ratio. We have checked that for various ionic strengths, and it did not seem to depend much on the ionic strength, which is a good sign actually. I mean, it does, the electric strength has an influence, but not the influence of the electron dose rate in combination with the ionic strength. So we go with 45. So the next slide may take some time to load. Maybe I should also. Yes, now we go. The options. Okay. Now in my screen it's not moving, so I will go back and forth once more. Yes, there we are. So here you see 8 movies playing at the same time. You see the stripy pattern because the scanning is not fast enough to capture the complete movement by the core. But you can see at the same time very well that sometimes the core is quite confined at the center of the shell, and sometimes the core is exploring the entire cavity of the shell. The most extreme cases are at the second one at 0.5 millimolar lithium chloride, where it's really confined more or less at the center of the core of the shell, and at the bottom right at 250 millimolar lithium chloride, so the highest salt concentration. It is really as if it's bumping from side to side inside the cavity. So it can explore the full 3D volume. Now, the remarkable thing here that in pure water, so without any salt, so the top left image, actually it has more room to explore than in the 0.5 millimolar case. So the question is, what is happening here with the electric double layers, and what is the situation with respect to perfect water? So first of all, it's remarkable that it's so stable. So the core never gets stuck to the shell, even at very high salt rates, when the bioscreening length is less than a nanometer. And actually here it is actually even like this, that the core is more often close to the shell than away from the shell. So it is like going around, maybe I can show that. It prefers to be, it is less often at the center of the shell, is more often closer to the shell because of van der Waals attraction. So here the attractions start to play a role. They are starting to dominate over the electrostatic interactions. But as a whole, yeah, it gives you a lot of information. I will come back in a minute about what is the difference between water and 0.5 millimolar. We have done a sequential analysis of all data. So at the bottom, you can see the sequence. We start with a binary mask, and then we mask the single frame. Therefore, we lose the information on the shell because that is not helping when you do analysis. Then we construct an averaged intensity of all frames. So you average over all frames. Next, we deconvoluted that image, and then we obtained a projected probability map. Okay, because it's the projected 3D probability. And the difference between 0.5 millimolar and 25 millimolar is very clear. So this is the procedure as explained in the paper. Now I'm moving on to the next slide. Here. So this is coming back to the remarkable thing that in water it explores the cell more than in the case of 0.5 millimolar. The point is, so the 0.5 millimolar, that is actually the normal situation. So when you look at the graph at the right-hand side, for the 0.5 millimolar, you see here the probability, the electric fields, and then you can see that it goes down as you go to the center of the shell, and it goes up again when you approach the other side of the cell. That is actually what you expect for normal electric fields. The point is that when there is no salt at all, the electric fields, the electric double layers, have a very long range, and this range is so long that they are actually overlapping. And because they are overlapping, you get a very shallow potential well, and the core has room to move around at this platform. It does not have a special reason to be contained in the middle. So this potential well is being lifted and becomes very shallow, and that is very unlike the normal situation. And that is the reason that in pure water it actually has more freedom to move around, because the potential is being lifted over the entire volume of the cell. While in the case of added salt, we are limiting the range of the electrostatic fields by increasing the ionic strength. We reduce the bioscreening length. And therefore it's more contained at the center of the shell. But that is not true, of course, for the higher concentrations of salt, because there the electrostatic potential falls off much faster, and that is why you get these platforms that are able to explore a larger fraction of the cell. Now, the reason that this is exciting is that we are able to determine from these experimental curves the real interaction potential. So the U is an energy expressed in kBT. So this is the first time actually that at the nanoscale interparticle potentials have been derived. So in panel D, you see the experimentally calculated potentials, and in E is the calculated potential. So there is some differences, of course, but the fact that we have been able to do this at the nanoscale is something remarkable. Now, trying to go to the next slide. So these are the conclusions. Rattle-type particles can be reliably imaged using liquid cell EM. The interactions can be followed at the nanometer scale. Double layer overlap is causing the particle to be able to move close to the shell at low salt concentrations. So that is the case of water. And this is a concern for stability, especially for nanorattlers. So if you want to build this into applications, it's really wise to add salt. And the core particle is stable even at incredibly high salt concentrations. So it never gets stuck, which is a good thing. The next step is electric fields. So can we really control this motion? So the motion so far that we have seen of the rattles is random. So there's no 3D preference. So it's confined in the shell at the center and less to the sides, but there's no directionality involved. So we have used electrodes. Basically, they are developed for electrochemistry, but we have used them here to subject the rattlers to an electric field. Of course, we have to make sure that the visible region is in the window region. And what we can do is manipulate these interactions with electric fields. So when the electric field is on or off, so in the off situation, the movement is random. Maybe it's confined a little bit at the center, but in principle, it's random. When the electric field is on, you can make them move in a parallel motion or in an orthogonal motion, or you can also find conditions where it's again random. I'll show that in a minute. So for this, we have used silica at silica rattles. So here the cores are also made of silica. Yes, I will not go too much into details. Then this is what you get. So if there's no field, so the panel at the left, the movement is completely random. If you apply a field of 1 kilohertz, then the direction is parallel. So it moves in the direction of the electric field. So from left to right in projection. At some point, you get a transition when there's a transition to an orthogonal field. And that means that the movement starts to become diagonal. Okay, so it's not random in one of the directions anymore. It is determined in two directions, but they both play a role. When you go, that's at 4 kilohertz. When you move to even higher frequencies, 20 kilohertz, it starts to move only perpendicular to the electric field. So that's the orthogonal direction, as we call it. And if you go to very high electric fields, so very high frequencies, then it again becomes random. Now, the reason that it becomes random at very high frequencies is because here the movement is regulated, is limited also by the ability of the ions to respond to the electric field. Okay, so if the electric field is switching too fast for the ions to move around, then at some point it becomes random again. Now, this is all very complicated, and the paper is in the review at this moment. I will not go into details, but it is impressive. So trying again to go to the next cell. So these are the movements, a bit more analyzed. Parallel means it moves from left to right, orthogonal, perpendicular to the electric field, and finally random. Of course, you have to tune also the electric double layers in such a way that it has the ability to move this way. So there is also, I can't see my mouse anymore. Let me see. Yes. Yeah, because of the very large number of movies, the Switching to the next slide is a bit slow. Yes. Okay, now I will not go back to the previous slide because otherwise we don't have enough time. But we have also checked the influence of the salt concentration. As I said, it's really the reason that these interactions are so complicated is because the ions are in the liquid are responding to the electric fields that are applied, and the switching of the electron fields, how fast can the ions move, do they have time to reach a particular equilibrium or not. And what you see is that, so for low kilohertz, yeah, but it does not have a very strong influence. So we checked it for 0.2 millimolar, 2 millimolar, and 25 millimolar. There is an influence of the salt concentration, but it's really the frequency, the AC frequency of the field that is by far most important. Only for the very high 25 millimolar, you can see, for example, that sometimes it becomes more random. We did not check all frequencies for the 25 millimolar. I'm trying to go to the next slide again. Yes, so this is the summary for the Rattle-type particles. The volume the core explores in the equilibrium can be tuned via the salt concentration. It can be changed also with an AC electric field. And by tuning both the salt concentration and the electric field strength and frequency, we can make a switchable colloidal crystal at the nanoscale. And that is again a spectacular thing. Good, so these were the Rattle-type particles. I still have some time to talk about p-NIPAM. Trying to go to the next slide again. Yes, they're playing. And now I'll go to the next slide. Yes, so one other thing that so these were particles that were confined in a sphere. But what can we do also with free particles? Can we also induce self-assembly by applying electric field there? So what we saw, and that is so close to the electrode, you should be careful with conclusions. And this was taken close to the electrode because there are always strange things happening there. But in principle, we can align cold nanoparticles and titania nanoparticles by applying electric field in free volume. So that is also nice. This is also known at the microscale, but it is not yet a controlled experiment. This is something that we want to expand on in the future, but it's a nice preliminary result. Now, thermoresponsive p-NIPAM particles. So NIPAM is a polymer, p-NIPAM is a longer polymer. And these are particles that are very often used in the chemical industry, in the food industry, because it also as a coating, by the way, because it allows you to control the size. And that is very powerful for all kinds of applications. So in a swollen state, it takes up more volume, all immersed in water. And when it's collapsed, it contracts and it uses less volume. And this transition temperature is at a very convenient 32 degrees, which is typically called the LSTC. So this is the transition temperature. And what we would really like to have is to see, to visualize this on a single particle level. So it is a very important transformation, and you can follow this process by the dynamic light scattering. That is also how this graph was created. But to image that is going to be very difficult because in a swollen state, it has almost the same density as water. And in the electron microscope, we depend really on density differences in order to see anything. So the top graph is the graph that we obtained from the dynamic light scattering for the p-NIPAM particle diameters. So these are polymer nanoparticles. At the bottom, you see two cryo-EM results. At the right-hand side, so at the bottom right, these are silica particles coated with p-NIPAM, and the other image is also cryo-EM, but this is pure p-NIPAM. So the p-NIPAM consists of a kind of more stiff core, where there is more cross-linking, and a kind of corona which is less dense. And this corona is actually the thing that is expanding and contracting as a function of this temperature change. And to image at the single particle level, such soft polymers are extremely radiation sensitive. So we have to come up with something. The particles in general shrunk. The moment that you start looking at it, we tried different dose rates. Of course, that helps if you use a lower dose rate, but still there's a shrinkage of the particles, and also did not respond at all to the temperature treatment. Okay, so in no time with the electron beam, you will have degraded the particles. The image at the right-hand side is a STEM image, obviously. Here you see particles that were in the viewing area. These are the bright particles, and particles that have diffused from outside the viewing area after drying. And there you can see very clearly that the non-irradiated particles are much larger than the irradiated particles. So they were irradiated in the liquid cell, but this image was taken afterwards after drying. And that is simply because of the huge number of radicals that we are creating just considering the water. So a list is given here at the right-hand side, and that leads to additional cross-linking. Cross-linking means that it becomes more rigid and more dense, and that it cannot expand any longer. So we need other strategies for the imaging here. So we used many things. We used radical scavengers. That's known to help sometimes, but it did not help in this case. Coating with metal precursors, gold, copper, but we just got enormous growth of all kinds of metal structures, and also the responsive behavior did not help at all. Altering the contrast of the solvent, for example, by adding uranium complex, also that did not help because also that started to precipitate at the particles and also fixing the particles. We also tried to flow in silica particles. That did help, but the contrast was very poor. So in the end, we made a combination. So we used tracker particles with gold cores and silica shells. These kind of automatically assemble at the corona, at the p-NIPAM particles. So on the left-hand side, you see the particles at room temperature. So you see actually in the liquid cell only the dense corona, and you see a shell around with the gold particles. They are surrounded by a silica shell, and they are like in between the ends really of the p-NIPAM strings. And that gives you an indication of how large the p-NIPAM particle really is. So when you go then to above the transition temperature to 40 degrees C, you can clearly see the contraction. And of course, we need some statistics here, but in the end, so the top result here, the DLS, that's dynamic light scattering, that's for a very large collection of nanoparticles. And this is at the bottom for LC-TEM. So this is for, so in the liquid cell, we can see here the thermoresponsive behavior. Of course, it dies out because it's so sensitive, but the fact that we have been able to see the contraction and expansion again is very powerful. Good, that brings me to the end. First, I would like to acknowledge Alfons van Bladeren, who has been very helpful in everything, the physical chemistry and the colloidal interactions. Tom Welling, who worked on rattle particles, Albert, who worked on the p-NIPAM particles for about 2 years, I think, before he finally succeeded. Arnoud also for his help with the electric fields interpretation. Sina he's part of our team for the liquid cell, and our collaborators from Tohoku University. And of course, Gelinde Moes and Fabian Hagemans for the synthesis of the p-NIPAM particles. So that brings me to the end of this talk, and I'm happy to take any questions.
Thank you, Marijn. Very nice talk. So now we have time for questions. If you want to address a question, please unmute yourself and go ahead.